the metric traveling salesman problem. Okay, now the usual traveling salesman problem does not require that its cities satisfy the triangle inequality. This might be a little bit surprising, but in fact, if you look back into Karp's original paper, it nowhere says that this needs to be a reasonable input. So now we modify this a little bit and look at a traveling salesman problem that satisfy the requirements on a map. That means distances should satisfy the triangle inequality. So if we have cities A, B, and C, then the distance from A to C is bounded by the distance from A to B plus the distance from B to C. So if we go directly from A to C, it's quicker typically than if we make a detour through another city B. So in general, the shortest path between two cities is the direct route. So if we have a traveling salesman problem that satisfies this triangle inequality, meaning that we have cities with distances as given on the map, well then this metric traveling salesman problem is still NP-hard. So now, depending on what you are modeling with the distances, an application may or may not be satisfying the metric condition. So, but we are going to look into this metric traveling salesman problem here a little bit more closely, because at least for trucking companies, this is the one that's more relevant. Okay, now we want to devise an approximation algorithm for this metric traveling salesman problem. So as an input, we are given a set of cities and distances between any pair of them, such that the triangle inequality is satisfied. Then we create a complete graph where the set of nodes is the set of cities, and the weight on each edge between the two cities is the distance between the two cities. Then we compute the minimum spanning tree of this graph that we just created. Then in a way we are going to explain in the next slide is we are going twice around this minimum spanning tree to get a tour, and this tour will have duplicate. So then we remove these cities that we visit more than once and get then a tour which goes to every city precisely once. Now it's perhaps best if we look at an example to see how this goes. So here on the left hand side you see certain nodes in a graph, and so this is a complete graph, but I didn't draw all the edges, but here is a minimum spanning tree. Okay, so this complete graph is labeled with the distances, and we picked here something where you go the sum of the weights of these edges is minimal. Okay, now what we do is we start at a certain node and then do a depth first search traversal of this tree. Okay, so in this case what this means is the following. We go from 1 to 2 and then go back. So in fact what we did here, to be precise, is we created a multi-graph where we doubled each edge. We go down here on this edge and then back, and then down this edge, this edge, this edge, and then back here, and then over here to the 6 and back, and then from 4 to the 3, from 3 to 1, then to 7 to 8, then back to 7, and then back to 1. Now, this is then an Eulerian tour of the 2 multigraph. And now obviously our goal was to find a way of visiting every city once, and obviously we don't need to visit cities multiple times in between. So whenever we have seen a city already, we're just going to skip it. Okay, so that means in our case we go from 1 to 2, and then we skip going back to 1 because we can immediately go to 3, and then we go to 4 and 5. We don't go back to 4, but we instead go directly to 6, then to 7, then to 8, and then return to 1. Now, obviously, because of the triangle inequality, when we skip some corner like this and go directly, then the direct way is of course shorter than the 2 routes. Okay, now first of all, the running time of this is really good, right? So it's creating the complete graph takes big O of number of vertices squared time, and Kruskal's minimal spanning tree is big O of E log E, so that's big O of n squared times log n time overall. Now the more important question is of course, how good is the quality of the solution, right? So now what we claim is that the cost of the approximate solution is bounded by twice the weight of the minimum spanning tree by the triangle inequality. Now, as I already mentioned, when we go in a tour from B to C and then to A, well, if we go directly, right, then this way is shorter than the detour through C, right? So when the tour created by going around the minimum spanning tree is adjusted to remove duplicate nodes, then we get something which is less than twice the minimum spanning. Okay, now the weight of the minimum spanning tree is actually less than the weight of the minimum tour. Well, why? Because a minimum tour, if we delete one edge, is a spanning tree. Now the weight of a spanning tree must be, of course, be at least the weight of the minimum spanning tree, and it contains an additional edge. So the weight of the minimum tour is greater than the weight of the minimum spanning tree T. So now let's recap what we know. So the cost of the approximate solution is bounded by twice the weight of the minimum spanning tree, which is bounded by twice the cost of the minimum tour. So the approximate solution is at most twice the minimum tour, so the approximation ratio is at most 2.